Over here on Vision of Earth, does nuclear waste last millions of years? Nuclear waste is made of many isotopes. Nuclear waste is not a homogeneous substance. It is composed of many elements that emit radiation for different lengths of time. When a nucleus emits radiation, it changes into a nucleus that is slightly different. Over time, radioactive materials transform into other materials, eventually reaching a state in which they are no longer radioactive. For more information on this process, see our explanation of decay chain. The majority of the material in spent fuel, nuclear fuel, is a relatively stable form of uranium called U-238. It has a half-life of over 4 billion years, so it will be around for a long time. The next largest fraction of material is unspent uranium-235 and plutonium fuel with half-lives of 700 million years and 24,000 years respectively. Okay, now, primarily, most of the fuel in our reactors are in between 1 and 3% of uranium-235. And the rest is U-238 with a zirconium cladding on the outside to prevent oxidation. Now, during this process, 1% per weight of the spent fuel turns into plutonium. There is 70,000 metric tons of spent fuel in the U.S. alone. 1% of that is plutonium. Okay, so uranium-235 is 700 million years and plutonium is 24,000 years. Okay, now, deep isolation.
Hey, just checking your old heart.
Scared me.
What can we do for you today?
Well, my old sedan had died, and I am now looking for a replacement.
I know exactly what you need. Follow me. There it is.
To construct a waste repository, we begin by erecting a rig, 150 feet tall, on a small concrete platform. We drill a hole straight down several hundred feet until it is well below any aquifer. Then a steel pipe, called a surface casing, is inserted into the hole. Cement is pushed down the casing and up the space between the rock and the casing, providing an additional seal. This is standard procedure for oil and gas wells, but we won't be extracting anything. We're doing quite the opposite, using the drill hole to place waste underground. Once the surface casing and cement are in place, the hole is drilled thousands of feet lower to the kickoff point. Here, the direction of the hole is gradually curved over a distance of 1,000 feet until it is horizontal. Then it will be given a slight upward tilt to provide even more safety. This horizontal drill hole, a mile deep and up to 2 miles long, is the disposal section. Remarkably, the curve below the kickoff point will be so gradual that even an 8-inch diameter steel casing bends easily around the curve. When the casing is in place, it too is cemented. For the storage section, we chose a layer that is in or below shale, a rock formation that is so impenetrable that it has even held gases for tens to hundreds of millions of years. Once the drill hole is completed and lined, we are ready to dispose of the waste. Each canister is transported to the site surrounded by steel and concrete to provide radiation safety for the workers. It is placed in the top of a drill hole and lowered using a stiff cable called coiled tubing. Once it reaches the storage section, the canister is pushed up by the tubing into the nearly horizontal disposal section. The canister is unlatched, the tubing withdrawn, and the process is repeated to insert more canisters. Nuclear fuel is compact. Just 3 horizontal drill holes can store a lifetime of nuclear waste from a large gigawatt reactor. Once the horizontal disposal section is filled with canisters, the vertical section of the drill hole is sealed with a combination of bentonite, rock, and cement.
Okay, this is over at my Science Direct, and this is on microannulus. Microannulus, or channeling in cement. Microannulus occurs when the cement is emplaced and the casing is pressurized. When the pressure is released after the cement has set, the casing pops away from the cement sheath. This generates a gap or microannulus between the casing and the cement. This can also occur if excessive pipe dope or varnish is present on the pipe, which is on the outside. Microannulus, due to pressurization, primarily occurs opposite washed out portions of the borehole. Okay, so channeling occurs when the cement is in the annulus but does not completely surround or is not bonded to the pipe. This condition will not have proper fluid seal, which allows oil, gas, or water to pass up the hole outside the casing. Microannulus, on the other hand, may have a proper seal even though a small gap exists. So channeling makes its way up to the top where microannulus doesn't, and it doesn't necessarily mean that it will make it up top. It's very important to be able to distinguish between microannulus and channeling. Squeezing may eliminate the channel altogether. So squeezing. Let me show you what that looks like.
Renegade Services, a trusted name in completion and wireline automation technology, is expanding the fleet with the local expander annular squeeze tool. Even when following cementing best practices, cement bond integrity may be compromised, unaddressed. Well conditions or unplanned changes during cement job placement can allow microannuli to form and create a potential flow path to the surface. The local expander is deployed via electric wireline, making for a very cost-effective method to solve the problems, like microannuli, sustained casing pressure, surface casing vent flow. The simplicity of the design is the most compelling feature, consisting of only a casing collar locator and the local expander tool itself. Actuating the switch delivers voltage to the motor and then expands the knuckles with an exact amount of power to dent the appropriate casing size. The local expander is a durable tool using straightforward, simplistic operation to densify cement, stopping seepage to the surface and permanently repairing the well. Local expander is run into the well on wireline and positioned by a CCL for proper depth control prior to activating the tool. Multiple local expansions are installed per target area to ensure the elimination of surface leaks. There is no limit to the number of expansions that can be made in a single trip in the well. It is Renegade's recommendation to install 3 casing expansions per target depth interval and a minimum of 6 per well.
Okay, here we got what they're talking about is this microannulus occurs right here where the cement's supposed to bond with the casing, the steel casing. But that's not the only place it occurs. It also occurs right here where the cement doesn't bond directly to the well, or the borehole in the ground. So to fix this, they use this tool to basically crimp outwards the casing, which will say there was a gas, there was a channel, this microannulus through here, and gas was coming up. So this kink should cause that to stop right about there. But to me, let's see here, once they do that, that will add stress, lateral stress to this concrete, and surely it should crack through there at every point where they crimp that. Do you guys not agree? So what they do is, this has all been sealed. They send one of these lines down with like basically a sonar, and they check the concrete. That's when they know there's an issue. So they send this down afterwards. So this is after the concrete's already cured for 24 hours. They crimp it. There's nowhere for that to move. So there's got to be something that gives there, and there's going to be a crack that occurs. This is not a good idea to put nuclear waste down into something like this.
Local Expander completes the cycle within a matter of minutes and easily moves up to the next location. Rapid cycling between the target intervals make the Local Expander a game-changing solution to wellbore intervention and repair. Even with the casing deformations, the casing maintains the same burst and pressure rating with no change in internal dimensions. The annulus is permanently sealed. The well is repaired and ready to resume production, injection, or abandonment. Local Expander is a Shell technology licensed by Renegade Services and developed in conjunction with Shell.
So this is what they're suggesting. They go down through these many layers. They go down through these many layers. They drill down through here, and they put the concrete and steel casing in. Okay. Then they put the nuclear waste in. All the way down here to the end. Right? And then they cap it off. They just cap it off, right? Cap it off here, probably cap it off here. And then what? They leave. They leave. And they don't come back. Now, will they put this shaft on a map somewhere? Probably. But what happens as these layers shift and move over the years, and this concrete breaks down, and the steel oxidizes and breaks down and rusts and begins to get holes in it? What then? We have aquifers up here. Right? Aquifers up here. And they're going to drill down through them all over the place. And you don't think that water isn't going to seep in to it eventually, and then flow down in here and fill up this whole thing? No? And then fill it up all the way up to the top? Or spread between the layers? Water from over here is coming over here, getting into there. Then now you have water in areas where it normally isn't. Usually it's only up here, right? They said, we'll get underneath where no water is. Well, what if this breaks down and water gets in here and leaks out through here? What then? Interesting, isn't it? Logic. Seems logical, right? Logic?
What is logic?